Hello everyone, and welcome back to the third lecture of this pulse measurement capabilities using Anritsu vector star and the pulse modulator test set. I'm Navneet Kataria. I'm the product manager for Anritsu vector network analyzers, and in the last measurement video we actually saw how to do a pulse profiling, plus we also saw how to generate various pulse configurations. So as I am showing you again here, we in the last video saw how to create singlet pulses, doublet, triplet, quadruplet, burst, and at the same time we also did a measurement in the profile mode for the pulse with our receivers in place and with the resolution of 2.5 nanoseconds, which is industry leading in the world today. So moving on, the next feature that I wanted to show you on Anritsu pulse capability is something called as point in pulse. Now, pulse profile that we studied in the last lecture is basically when somebody wants to see the overshoot, the pulse width of a particular pulse, and various other parameters related to pulse. Moving on, some customers also have a lot of interest in some points or some portion of a pulse. Now, as you know, there is a rise time in a pulse, there is a fall time in the pulse, you have ringings and overshoots as well. Now, because the pulse is made up so many things, the actual stable portion of the pulse is normally what people are interested in seeing them. So for that, there is something called as a point in pulse measurement, which we will be demonstrating today. So as you can see, with option 42 from Anritsu, we have the pulse view configuration. In the last lecture, I described everything about the B2 profile, the sync signal, which is basically a starting measurement signal for the vector network analyzer. Then you have 4 internal pulse generators, plus you also have an external pulse test set modulator, which can actually work up to 70 GHz with various configurations. Let me quickly so the last time that we did the measurement, or the pulse that we showed and played with, was this, right? Now let's move on to the pulse view setup configuration again, and this time let's analyze a point in pulse. When I do a point in pulse, basically because we are interested at a particular portion, so we have to sweep or maybe first things first, we have to select a data. Again, let me go back to the pulse profile again, so that I can actually show you which part of the pulse we are actually interested to see. So I'm making use of markers in the vector star. It's very straightforward how to use the markers. You can drag and drop them. So what I'm seeing here is that the flat portion of the pulse, as per my understanding, you can see that roughly starts with around 140 nanoseconds, and it's pretty flat till a duration of say 220 seconds, right? But before that, we have some ringing and overshoots, and then we have the drop time. So what I'm gonna do is, I would want to analyze, or maybe if I have a DUT or a customer has a DUT and he wants to see the pulsed S parameters behavior of that particular DUT, he would actually want to choose a flat portion of the pulse and then make the S parameter measurements. Now all the basic S parameter measurements are available in the pulse mode. So of course you'll have to do a calibration first with all the frequency points, and maybe using an automatic calibration kit, or by using a mechanical calibration kit, and then all the S parameters, S1, 1, 1, 2, 2, 1, 2, 2, whatever you want to do, that is quite possible. So now that we know our starting point and the stop point, which in turn basically is the width, the measurement width that we want to do, and we know that we have to put in a delay as well. So I believe from the starting 0 point, we can start the flat pulse measurement at 140 nanoseconds, and we can actually somewhere stop around 200 nanoseconds. So now that we know which portion of the pulse we want to analyze, let's go ahead and analyze that portion of the pulse. So I go into pulse view configuration. This time I select the point when pulse. My receiver is still the same because I'm using the same DUT as the last video, or the pulse demonstration module that I discussed in the last video. So now this time the measurement width is basically 100 nanoseconds, because we saw that we want to start the measurements from say 140 nanoseconds and we want to go to say 240 nanoseconds, or maybe we can start with say 120 and we can stop at 220 as well. That's not a problem, but I'll show you why that is required. So the width is roughly around 100 nanoseconds, and the delay that we want to do is say suppose 120 nanoseconds. Okay, that is what we chose. So you can see now that our pulse are overlapping, and this is the later portion of the pulse on the PG4 that you see this green pulse. We want to actually just focus on the flat portion of the pulse. So when I do these settings, I just click done here, and when all the settings are basically done, you'll see that it's a flat line, right? So right now it's analyzing that, but right now the frequency basically is from 5 to 15, and the CW mode is on. If I want to see an in-depth of what's going inside the pulse, I will have to make the CW off, and I'll see that okay, I can see some parameters like a pulse shape kind of signal, like a sinusoidal signal inside the pulse, right? So what I need to do is I need to narrow down to say a frequency of my operation. So I do a 9.5 gigahertz to say 10.5 gigahertz, and you'll see that actually now I'm seeing a pretty good shape of the CW signal which is forming that pulse, and my number of points are 51 only. Let me increase it to 501 points, and now you'll see that actually the power in that flat portion that I chose is roughly around -20. Now this is very important for the designers of various DUTs which are being used for pulse measurements. Now say suppose if the customer now wants, okay, in the flat region I'm pretty good, no problem, but what if my DUT is now seeing an overshoot portion of the pulse? In that case, what I can do is I can go back to this menu, or maybe let me just first save the data here so that we can do a comparison of the power content in the flat portion of the pulse, and then the power content maybe in the rising edge or the falling edge. So I've stored this to memory. I go back to my application menu, I go into pulse view configuration, and let's say instead of the delay being 120 nanoseconds, what if I do a delay of say 50 nanoseconds only? Okay, so that means now I would be somewhere in the range where the pulse is rising and it's also having a lot of ringing and overshoots. So if I do to say 50 nanoseconds, let's see what happens. So when I click done, now my frequency span is still 9.5 to 10.5, and you'll see that there is a slight power reduction in that range. So again, let me show you the memory and the trace. So data and memory, you'll see that there is a little bit of difference in the power. What if, say suppose now I go to again the pulse view setup, I go to pulse view configuration, and instead of 50 nanoseconds, let's assume that I take just at the rising edge of the pulse, say suppose 20 nanoseconds. Let's see what happens. If I do the delay of 20 nanoseconds, and remember there was a 50 nanoseconds delay because of the pulse demonstration module length, right? So if I do done, let's see what happens. What's the degradation in the power? And now you will see that from the peak portion where the power was pretty flat and the pulse was pretty flat, you will see that there is substantial power reduction. Now I can also see what happens at the falling edge of the pulse. And let me tell you everyone that these kind of measurements are actually very important for somebody who's trying to characterize their pulse DUTs. So actually our pulse was up to 200 nanoseconds. So let's see what happens at 220 nanoseconds. Now we are almost at the edge. There would be some energy content, there should be something. So let's see what happens. So when I do a 220 nanoseconds display, you'll see that the power now is very, very low and it's distorted as well. If I want to see what happens even further, if I do 250 nanoseconds, let's see what happens. Again, you'll see that now it's really, really bad and it's all noisy. So that means most of the times the customers who are trying to characterize their pulse DUTs, they would want to actually play in the region where the power is actually constant. So this is normally what people in different type of applications do. One more thing that I wanted to tell you here, and I just want to tell you that this is very unique to Anritsu. Right now we are just doing a 9.5 to 10.5 gigahertz sweep, right? But it may happen that the DUT may be operating over a wider frequency range. So let's see what happens here. If I have a 9.5 gigahertz to say 15 gigahertz, the overall power content is gonna be compromised. Now this is how it looks, but let's just go back to the pulse setup and make the setup back to say 100 nanoseconds, wherein we were seeing a really good power. So let's see what happens, but this time the frequency range is a little more. So you can see that I'm seeing a lot of pulses, right? Now it so happens that for a lot of customers, they are not satisfied with such a small frequency span. Now we have something called as a continuous profiling as well, in which the entire sweep for the entire duty and for the entire frequency ranges basically happens in one acquisition. And that is very important sometimes, and if you guys have those kind of applications, just let us know, and we can arrange for a demonstration for you, because that demonstration setup requires some more connections to be made, which I don't have right now on my VectorStar. But just want to tell you that we do have continuous profiling, and we also have continuous pulse in pulse mode as well. So going back to changing my frequencies from 9.5 to 10.5, I just want to see that everything is matching here. Yep, and now I can get rid of the memory. It's just the data that I'm seeing here. Now this was an example of a frequency sweep, right? What if a customer wants to measure an amplifier and the S parameters of an amplifier in the pulse mode? In that case, they will have to do a power sweep, right? So doing a power sweep again is very, very straightforward and very, very simple as well. What you need to do is just go onto your power channel, you go to sweep, and instead of frequency sweep, this time what we are gonna do is we are gonna do a power sweep, which is CW frequency. When I do that, you'll see that this right now does not look really well. Why? Because we are seeing the S21. What we have to see, because we have a pulse modulator test set in place, we'll have to see an A1/1, which is the test side, and then we'll also have to see B2/1, which is the receive side. So we go on to our response side, and instead of B1/1, we do an A1/1, which is basically the transmit side of our, and we can actually switch off the averaging. The averaging is not required. And to change the frequencies here, so right now the frequency is 70 kilohertz, because we are doing the measurement at a fixed frequency, because we are now doing a power sweep. So we have to change the frequency to 10 gigahertz, because that is where we want to characterize our DUT. And you will see that now we are seeing that the transmit side test receiver A1. But for us, what happens is that it goes through from the A1, which is the test side transmit side test receiver, then it goes through the dot, and then it goes to B2. So for us, it's also important to see what is happening on the receive side for the vector network analyzer. Right, so first we add in one more trace so that we can actually see. Again, we change this to just to log magnitude, not log magnitude and phase, so that, like, you know, just to identify two traces with different colors. And again, I go to response, and this time instead of A1 over 1, I do a B2 over 1, because that is what my receiver is seeing, and then frequency again is 10 gigahertz. Let me do an auto scaling here, and you see, and again, I don't want to do averaging, so I do an averaging off. And now you can see that when I have an overlay of the A1 over 1 and then the B2 over 1, you can see that there is a difference, but again, we can do a power sweep. By default, the vector star power sweep, which you can see from here, is from -20 to +5. There are some losses associated with the test pulse modulator test set, and that's why you are seeing these losses. But again, the whole aim of showing you this was that you can do a power sweep, and you can see all the pulsed S parameters as well. Now, one more thing that a lot of customers normally ask me is the fact that, hey, can we calculate group delay as well? So group delay is very important, because for the pulse kind of measurement, people normally want to see that what is the group delay of their duty for that particular frequency, so that they can actually, you know, try to match the receiver if there are any delays. So they want to take care of, or they want to actually compensate for the delays which are happening. So we can do that pretty straightforward. That's not something which is very difficult. Group delay measurements, again, the measurements are pretty straightforward. Now, as you all know, group delay is basically the rate of change of phase with respect to time, and that is basically a frequency domain measurement. So we have to go back and sweep the frequency again, not the power. The power work is done, and again, instead of A1 over 1, we actually want to see S21 measurements, and you'll come back to basically the same trace that we actually showed you for the graphs for the central pulse. So we can do a scaling as in auto scaling here. So we can do an auto scaling here, and basically you will see the same trace that we were seeing for actually doing a point in pulse, right? So now, instead of the measurement being log magnitude, we just have to change the measurement from log magnitude to group delay. And again, if I do an auto scaling here, you will quickly be able to see what is the group delay for your particular DUT. So this was the third measurement video that I wanted to show you, in which we basically covered as to how a point in pulse measurement is made. Now we have a lot of clarity that all the pulsed S parameters for an active or a passive component can be made. I am still using all the same setup and the same DUT. The setup comprises of a 40 gigahertz network analyzer with option 35 and 42 inbuilt into them. 35 option is for the IF digitizer, which actually gives us a 200 megahertz of IF bandwidth, so that actually we can do a resolution of 2.5 nanoseconds on various pulses, which again is industry leading. And then I'm using a pulse modulator test set again in this measurement setup, plus my DUT or the pulse modulation. Basically where it is happening is in the pulse demonstration module, whose specifications are already available, and we discussed on that in the last video. So this is what I wanted to show you for this time. Thank you so much for tuning in. In the next measurement, we will see how we can do a pulse to pulse measurement as well. Again, thank you so much for listening, and stay tuned. Thank you.